you're already here, I guess we'll go ahead and get started on another General Chemistry 1 video today. So today, it looks like I've already prepped for talking about atomic spectroscopy. This stuff is actually really cool. I'm only going to talk about it just a little bit, but you will go over it more later. Also, be sure that you are reading your lab manual before you watch the rest of the videos. So, the very first thing I want to talk about is what are we looking at when we're looking at atomic spectroscopy? Well, we are looking at spectral lines. And what that means is that we have each element, it has a set number of electrons, and they are in a certain ground state. They're just kind of chilling, going around here. They don't actually look like this, so when you get into OChem, don't be like, Andy drew it on the board wrong, here's a video of her doing it wrong. I know that they don't actually look like this, but for the sake of making this simple, this is what we're going to say that an atom looks like. So over here we have this atom with an electron just chilling in the N ground state. Well, I'm going to come over here and I'm going to take a photon of light energy, and it is just going to come along here and it is going to excite this electron up to a higher energy state. Now, this energy state is less stable, so this electron is going to want to go back down to its ground state. When this electron travels back down to its ground state, it releases light in a certain spectrum. We are going to be looking for those distinct spectral lines for each type of molecule that we will be analyzing throughout this lab. I hope that makes sense. I promise it will. Okay, so something to keep in mind, and you will talk about this more when you are doing your calculations with your TA, but you need to pay attention to the higher state because your N initial will always be bigger than your N final. Your N final is going to be this ground state. Your N initial is going to be the excited state. So don't get confused by that because we can't actually see this first part. We can only see it when it's letting stuff off. So we start about halfway through what's happening when we do our calculations. All right, so you saw some pictures of our lovely TA Cece using one of our spectroscopy little telescopes. And she was looking at helium light in that spectroscope. When she was looking through that, this is what she was seeing. She was seeing a scale from 4 to 7 with different lines. These lines are part of helium's emission spectrum. Now, helium has a literature emission spectrum that we can see here. If we can just zoom in a little bit on this emission spectrum, we can see that there are lines out here. There are some stronger lines in the red and yellow range, and the blue, violet. When we are using the spectroscope, they're a little bit harder to actually see. So when we were looking through it, this is what we were seeing. Now, we didn't have all the colors for the markers to make this super accurate, but you can see here, she saw blue that was medium at about 4.5. She saw yellow that was strong at about 5.5, and she saw red that was medium at about 7. Wonderful. So then we can come to page, I believe it's 99 in your lab manual, and we look at this table. And where we saw red that was medium, so right here, we know that that correlates to 678.9 nanometers. So that is the wavelength of that light that's given off. If we go down to yellow and we say yellow is weak, well, we can say, okay, that weak yellow is 587.6 nanometers. And if we go down to blue, that is going to be 447.1 nanometers. It is those numbers, those wavelengths, as well as the light that you see, that you are going to use to calibrate your spectrum. So if we know that we have red of medium strength at 7, we know that 7 is going to be equal to 678.9 nanometers. That is the wavelength of light at that spot on that spectrum. We do the same thing with 5, so we say our yellow strong, which is here. This is going to be 587.6 nanometers. And our 4.5 over here, where we had the blue medium, that is going to be equal to 447.1 nanometers. So that is the wavelengths of light at those spots. You will then use that to make your calibration curve, where you have your spectrum here, right? And you have your wavelengths over here. So if we said we had 4.5 and we had 447, we would put a point there. 5.5 is going up to 587, let's just say that's here. And we have 678, or we have 7, and that would go up to 678 point here. That creates our calibration curve. When you make your calibration curve, make sure you're adding in things like your equation of the line and your R-squared value, because that's what you will use to answer subsequent questions. The next thing we need to talk about is the salts that we burned. So we burned some salt, we got some colors, that was fun, but there were some unknowns that you will have data for. Those unknown data is gathered by burning something that is either strontium or lithium and looking at it through the spectroscope. We then find the spectral lines, and we will compare those to the literature values of lithium and of strontium. So the literature spectrum of lithium is given here, and the literature spectrum of strontium is given here. You will also have data for lithium and strontium that were looked at through the spectroscope in lab. So just like helium, you won't necessarily see all of the spectral lines for either lithium or strontium because we just don't have the capabilities to do that in this lab. Instead, what we've done is we have taken strontium and lithium and we have looked at them through our spectroscope that we've calibrated with our calibration curve. And we have found the literature values for those and made them ourselves in lab with the equipment that we actually have. When you look at your unknown, you will then compare the lines that you are given or the observations that you're given for that unknown, and you will compare them to the observations that were given to you for strontium and for lithium, and that will give you a way to figure out what your unknown actually was. I hope that makes sense. If not, shoot us an email. Khan Academy is great, and have a wonderful rest of your week.